All right, so there are different kinds of random variables, and so we have three different kinds. One is a finite discrete random variable. Okay, so that just means that the random variable assumes a finite number of values. So, for example, if the number of heads in three coin flips you saw in this last example, you could get 0, you could get 1, you could get 2, or you could get 3. Um, you could get 3 heads in 3 coin flips. So that would be an example of a finite discrete random variable because there's a finite number of outcomes that the values that the random variable can assume. All right, so we can also have an infinite discrete random variable. So in this case, it's the outcomes are still discrete values, but there are infinitely many of them. So let me give you an example of that because that sounds a little strange. So let's say you flip a coin and you want to know, if you're interested in the question, how many times do I have to flip this coin before it comes up heads? Okay, now that's going to vary, right? It might take 1 coin flip, it might take 2 coin flips, 3, 4. We don't really know where it could end. I mean, in theory, it could take an infinite number of times. We don't really know when it's going to end. So it's instead of being finite discrete, it's infinite discrete because we don't have a finite set of values. Okay, and the last type of random variable is the continuous random variable. So this is one where our outcomes are not discrete values. It might be, for example, a case where you're analyzing supermarket checkout time. Okay, so it's not like it's going to take either 1 minute or 2 minutes or 3 minutes. It might take 1 minute and 15 seconds. It might take 3 minutes and 17 seconds. All right, so really that wait time can assume any value on a continuous time scale. All right, so just like if you recall from the last chapter, chapter 7, we assigned probability distributions to the outcomes of an experiment, right? We used sample points, which were all the individual outcomes that were mutually exclusive, and we assigned probability values to each one of those simple events. Okay. Now we can do the same thing with a random variable, right? Because essentially it is a proxy for the outcome, right? Where we are, taking the outcome and then assigning a numerical value to the outcomes. So just like we can have a probability distribution for the simple events, we can have a probability distribution for the random variable as well. And the same rules apply as before. The probabilities are going to be between 0 and 1. So each probability for each random variable is always going to be between 0 and 1 inclusive, right? For each particular random variable. So they're calling x1, x2 all the way up to xn. Those are the values that the random variable assumes, and the associated probabilities are p1, p2 through pn. So in general, the general probability is pi, where I is equal to 1 or 2 or 3 or whatever up to n. Okay, we also know, if this represents all the possible outcomes, that those probabilities are going to add up to 1, right? So P1 plus P2 plus P3 all the way up to Pn. We take all of the random variables and sum up their probabilities. We're going to get 1, right? Because there's 100% something's going to happen. Okay, so really these rules are no different than the rules we learned in chapter 7. It's just now that we're applying them to a random variable. Okay. So let's go back to example 1. So example 2 is actually looking back at example 1 and assigning a probability distribution to the information that we created back here. So let's take a look at this. we had we took all the possible outcomes, we assigned numerical values of them. Now to them. So you notice that 3 only happens once. There's only one way we can get a 3 heads. And that's the heads case. The same way with 0. There's only one way to get 0 heads, but there are multiple ways of getting 2 heads or 1 head, right? So we have 8 possible outcomes, right? 1 out of 8 of those is 3 heads. So we can actually write all those possible outcomes or all the possible values for our random variables, right? We either got 0 heads or 1 head or 2 head or 3 heads. And 1 out of 8 of those is 0 heads, right? So 0 heads, that would be tails, tails, tails. So there's a 1/8 chance of getting this particular random variable of 0. And the same way with 3 heads. The only case where we get 3 heads is heads, heads, heads. There's only 1 out of 8 possible outcomes that's heads, heads, heads. Okay. Now the others, notice for a random variable of 1, we have 3 different ways, 3 different equally likely ways of getting 1 head. Okay. So 3 out of 8. So our probability down here for a 1 is 3 out of 8. All right. And the same way with 2. Basically the same. We have 3 different ways that we could get 2 heads, right? We either get 2 heads in the tail, we get the tail in the middle with a head on either end, or we get the tail and then 2 heads, okay? But those are all equally likely outcomes, and so there's 3 out of 8 equally likely outcomes that give us a random variable of 2. So 3 out of 8. Now notice, if we add that up, right, because we've got all the possible outcomes, all the possible random variables that this experiment could assume. So if we add 1/8 plus 3/8 plus 3/8 plus 1/8, we get 1, right? So that's good. All of our probabilities add up, and all of our probabilities are between 0 and 1. Okay? All right. Well, I will meet you in the for the next example.